In the last video, we introduced the idea of static friction. So now we can introduce the idea of kinetic friction. So that would be if it is moving. So, so we have kinetic friction. So if it's moving, then you're sliding past. And so again, you have friction because you got to keep a force on it to keep it moving at constant speed. And so there's a frictional force that resists the motion. I'm going to put F sub K for kinetic friction. Now, what happens though is the microscopic level where these surfaces are moving past, they don't get a chance to lock in as well. And so kinetic friction tends to the coefficient of kinetic friction tends to almost always be smaller than the coefficient of static friction. And it works the same way. If I push down on the object, then it locks these things together, so that means that the kinetic friction is also proportionate to the normal. And again, proportionate here. Now, the difference is this is actually an equality here. This is not an inequality. So the kinetic friction is equal to the coefficient times the normal force. Now, the interesting thing is that if you have an object here and the object has the same surface conditions and the same coefficient of kinetic friction, then to a first approximation, the area here doesn't matter. The smaller area has the same force on it, but it's over a smaller area, which means that a greater portion of the force is in each one, so that means each part of it gets more, but there's less of it. The end result is that the kinetic friction here is the same as the kinetic friction there, even though it's got a smaller surface area on the right. This is experimentally verified. Again, it's to a first approximation. One thing that does happen is as you're sliding, you're doing more damage to the surface on the smaller surface. You're concentrating all the damage in one area, and once you're damaging the surface, that does change the surface conditions. So after a while, you start changing the coefficient of friction, which does change how much friction you have. And so, but you know, to a first approximation over the time interval that we're dealing with typically in this class, then we would say that the surface area doesn't matter. So let's do a couple of examples here with kinetic friction. So let's say that we've got an object here, mass m, and it's moving with some initial velocity v0 equals 1.5, so 1.5 meters per second. Okay, so 1.55 meters per second. And then what's going to happen is that there's a coefficient, so this surface is slightly rough, so we'll say a coefficient of kinetic friction of 0.350, and I want to know how far does it go until it stops. Okay, so you look at it and say, okay, well, that's fairly straightforward. The distance is x0 plus v0 t plus 1/2 at squared. Okay, so we'll say x0 is 0. V equals v0 plus at, so the final velocity is 0. So that means that that t, the time that it takes to stop, is going to be minus v0 over a. Okay, and so if I plug that in here, x equals v0 times minus v0 over a plus 1/2 at squared. So this is minus v0 squared over a plus 1/2 a v0 over a squared. So this comes out to be equal to v0 squared minus v0 squared over 2a. Okay, so all we have to do is now figure out what is a in this problem. And so how do we find A in the problem? Okay. So well, you look at it and say, well, so x equals minus v naught squared over 2a is going to be minus 1.55 meters per second squared divided by 2 times minus 3.43 meter per second squared. So x then comes out to be 35 centimeters, 0.35 meters. Okay, so this is an example of sliding motion and example of kinetic friction.